Stephen, I saw your slides. Do you want to run a little bit to see to test it out?
Okay, and the slides are properly sharing right now?
Yeah.
Okay, great.
Yeah, perfect. Okay, without further overview, it's my great pleasure to introduce Professor Stephen Boyd. Stephen is the Sampson Professor of Engineering and Professor and Chair of Electrical Engineering at Stanford University, also with courtesy appointments in computer science and management science and engineering. Stephen has done a lot of fundamental work in convex optimization. He's also author of many seminal work in this domain and also several books, including the popular and beloved convex optimization book, which I think everyone reads. His group has also developed several open source tools like CVX and CVXPy that are widely used in academia and the industry. His current research focus is on convex optimization applications in control, signal processing, machine learning, finance, and circuit design. Today, he's going to talk about embedded convex optimization for control. Stephen, the floor is yours.
Great. Thank you very much. Let's see, I also wanted to say that unfortunately I was teaching just until a few minutes ago, and so I didn't get to join until now. So I won't be able to relate what I'm talking about to some of the previous talks, which I know, in fact, were quite relevant. So I'm going to talk about embedded convex optimization for control. And this is, I mean, the slides were assembled by me and some of my students, in the case of Shane, former students. So let me say a little bit about the talk. So the first is that the math is going to be sloppy, and I'm going to talk a lot about just ideas. And they're not even complicated ideas. Occasionally, I'll issue opinions. Some of them will actually be a little bit controversial, I hope. And also, I'm not going to spend my time saying who did what when. So I'm just going to talk about a lot of stuff that was done by other people, and I won't say anything about it. So, and finally, I won't have any fun videos or cool examples. So not because they don't exist, but because I just wanted to talk about the ideas in this talk. So first I'll talk about convex optimization control policies. So the basic idea, it's not deep or anything, it's just this, that a lot of control policies are based on solving a convex optimization problem. And so we're going to call these, well, COCPs, or convex optimization control policies. So some examples would be things like LQR, linear quadratic regulator. I'll say something about that in a minute. Generic convex control, things like approximate dynamic programming in the right context. MPC, or receding horizon goal, or RHC. Things like, it's often used in single and multi-period trading in finance. I'll talk about a couple of other very useful problems, things like actuator allocation and real-time resource allocation. Now, a couple of these are analytically solvable, like the linear quadratic regulator, but our focus is actually on the others, where you actually solve, to evaluate a control policy, a real convex optimization problem without an analytical solution. So we'll start with a case where you can. That's traditional quadratic control. So here you have your linear dynamics here. X is your state, U is your input, and WT is some disturbance that's zero mean. We have a convex quadratic stage cost. This is all traditional. This is from 1960. And what we should do is find a policy, UT, which is a function of xt, and it should minimize the average stage cost. Now, the optimal policy, that's a linear quadratic regulator, has the following form, that what you should do is you should minimize the immediate cost. X is already fixed, xt, that's a fixed cost, so I don't have to put it here. Plus, basically, this is something like the cost to go from where you land, and I should optimize over my what I can do over the sum of those two. Now, this thing that you're minimizing here is a convex quadratic function, and so it has an analytical solution. And so most people think of just simply writing it this way: ut equals kxt, because the solution of if you have a quadratic function and you minimize over one variable, in this case ut, the result is a linear function of the remaining variable xt. And so you think of it this way: you get a linear policy. But I claim this as a COCP, convex optimization control policy. Now, we can also just do very general convex control. So here, suppose my dynamics are linear or affine in the state and the control, that's xt and ut. Omega t is some disturbance. Those are IID. And suppose the stage cost is convex in x and u. It doesn't have to be quadratic, just convex. And your goal is to minimize the expected average stage cost. Well, the optimal policy is, once again, it comes from dynamic programming, or Bellman's formulation. It's this: you should minimize the immediate cost plus the cost to go. That's the Bellman or value or cost to go function v of f of xt, u, and omega t, and you should take in expectation. So you want to minimize the average of that over u. And here again, this function, the expected value of the immediate stage cost in the second term, which takes into account the future, that's a convex function, right? Because convexity is going to play nicely with expectation and sum and stuff like that. So here is an example of a convex optimization control policy, just generic optimal control in convex control. Now, maybe more useful is approximate dynamic programming. So here, what you do is you simply substitute here for the true value function, you substitute some kind of an approximation. And this approximation, you're going to choose it with two ideas in mind. Number one, it should capture the general shape of the actual true value function. And the second part is it should make this optimization problem where I minimize over u, this expression, I should make that thing should be tractable. So I can do that in real time, right? So that's the idea. And this requires only that f is affine in u, not x, and g is convex in u only. They do not have to be, they don't have any curvature with respect to xt or anything like that, or with respect to x. Okay, so this is approximate dynamic programming. And I guess I don't mind mentioning, since everyone here is in control, that I feel like one of the dirty secrets of control is the following, is that, this is going to give you a really good policy if V hat is a good approximation of V. That's sort of obvious. But here's one of the dirty secrets. It turns out you get a really good control, even when V hat is a rather poor approximation of V. V hat only really has to capture kind of the gross shape of V. Now, people know this, everyone knows this, but people don't state it that often. But once again, this is obviously a COCP, a convex optimization control policy. Next up is another extremely practical method, model predictive control. So here, the dynamics function is affine x, u, stage cost is convex, and x and u. And what we do is we do something kind of ridiculous. We make a single prediction or forecast of what these uncertain variables are. If those were zero mean things, the most common forecast is just zero. So what you do is you minimize, you pretend that there's no uncertainty over some horizon h periods long. You pretend that there's none. You pretend that your forecast is what's really going to go down, and you make a plan based on your forecast. And you do that by solving this problem here, which is a convex optimization problem. So you plan a full trajectory over the states and the controls over this horizon, and then you only use the current state. You just use the current control, and that's the policy. So that's another convex optimization control policy, because you evaluate the policy by minimizing a convex function or solving a convex problem. Now, there's been a lot of work on variations on that, on making this robust. I'll mention one that as a practical matter, as a theoretical matter, is extremely unsophisticated, and as a practical matter actually does really well. And it's just, multi-forecast model predictive control, which I guess we call, or we're trying to propagate that it should be called MFMPC. And yes, that is a joke. All right, so you have multiple forecasts. So we're going to denote these as omega I hat tau given t. That's the prediction of what will omega be under forecast I at time tau, and it's the forecast made at time t. And we think of these as scenarios or contingencies, right? These are just, and the only real requirement is that these should be plausible. When you see these forecasts, it should not be that someone would say that could never happen. They should simply say that's reasonable. And you can make this statistical. Actually, I think that's a little bit silly, frankly. That's over mathematizing things, but nevertheless, that's it. So now what you do is this. You make a plan for every single scenario, and you add a single constraint that the first action is the same. So this is actually equivalent to doing, to basically relaxing the original information pattern and making it very elementary. It's basically, number one, there are only k things that can happen. That's the first part. And the second part is, after you commit to your first action, then I will tell you which of the k occurs. So that's the information pattern for which this would be optimal. I mean, it's silly, but the point is that's an interpretation for it. Okay. I'll mention a couple of more practical ones, not generic ones. Single period trading. So in that, your job is to choose an asset allocation weight. These add up to 1. They don't have to be positive, though. They can be negative, which corresponds to short positions. So the idea is that we are going to choose WT, I should say we're gonna choose trades. We'll let WT is our current one. I'm sorry, W tilde T is going to be the post-trade allocation. That means, so the trades will be something like W tilde T minus WT. And we're going to maximize a composite objective that has got a couple of terms in it. The first one is the expected return. So alpha T is a forecast or expected return, right? Actually, forecast is a more accurate way to say it than expectation, right? Expectation requires you to believe that these are actually random and that there's a mean and all that kind of stuff, all of which is false. The second term is a risk aversion term. So here, sigma t is a forecasted return covariance. And this second term is going to be the forecasted variance of the total portfolio value, right? That's this term. And there's a parameter gamma called the risk aversion parameter. And the more you turn that up, the more you will choose a W tilde for which this is small. The last two terms are a so-called holding cost and a transaction cost. And they are really essentially penalties or objective terms that depend on roughly the portfolio and change in portfolio. Transaction cost is change in portfolio. And the holding would include things like a shorting cost or something like that, if there's a cost to holding something. Anyway, so that's what that is. And when you take this and do the multi-period version, you get something called, multi-period trading. And that's an example of a specific convex optimization control policy. Okay. I want to mention a couple of others which are super duper simple, but actually also like super useful. So the first one is actual actuator allocation. So the idea is that a high level control policy produces the desired and forces and torques. Let's call that FT. So I guess you call that a wrench or something. And so you would get the forces and torques that you would like to apply, let's say for the next 15 milliseconds. And then the question is how to apply it. How to achieve those forces and torques, right? And so actuator allocation says you should solve a little problem that looks like this. You should minimize GT of U. That's some convex cost function. It could have fuel use, energy, whatever you like in it, this kind of thing. Plus lambda times U minus UT minus 1. UT minus 1 is the actual actuator value from the previous time. Right, and so, and what this is simply a smoothing term, and it's subject to the fact that the actuator vector you're choosing is allowable, number one, and then this is AT is what maps your actuators into your forces and torques that you put on whatever the system is, right? And so that's the basic idea. And this actually, I mean, this is kind of obvious. It's very simple. There's no theory of any kind whatsoever here. But actually just having something like this gracefully handles all sorts of stuff. Actuator failure, degradation, varying effectiveness, right? So for example, I mean, even just the simplest things, a lot of actuators are, tied to a body frame or something like that. And so the absolute force and torque is going to depend on the orientation of the vehicle, right? So that's going to be embedded in AT. If you have things like actuator failure, degradation, that's real simple. You just change the UT set. You just simply say, oh, hey, guess what? Your, thruster number 7, it's not working. So, and that means that in the U7 is going to be 0 or something like that. And this thing will do perfectly well there. Okay, so, and actually that's actually a perfectly, that's a really good use just to have something like this. So that's actuator allocation, very simple, super useful. And it is a method that it maps a required force and torque. Given that, it figures out how to actually achieve it with the actuators that you have right now. Okay. One last one I'll mention is a real-time resource allocator. So the way that works is you have M resources, which are to be distributed across N agents or tasks, right? So for example, at a data center, you have resources like, power, number of cores, the total number, the amount of IO bandwidth you're going to allocate to each of your agents or tasks, things like that. The amount of memory you're going to allocate to each of them, this sort of stuff. You have available resources, which can be changing with time and also unexpectedly. And the action is a resource allocation. That's a matrix. And what it does is it tells you how much of each resource you allocate to each agent or task. So that's the idea there. Okay, and we're going to solve it by maximizing some kind of utility, which is a concave function. And usually it's separable across tasks, but it certainly doesn't have to be. And then subject to the fact that these allocations are non-negative. And this says that they add up. If you look at the total resources you are using, that's U1, that vector, is less than AT. That's a vector of what is available at time t. And that could be varying as well. And again, outside your your control, right? That it's simply announced every second what the total amount of resources you have, and you have to allocate it, right? So again, simple, this is static. You couldn't call this a control problem because there are no dynamics, but nevertheless, it's an important part, I believe, of control. Okay, so at this point, what I'll do is talk about the general form. So the general form of a COCP is that the action UT is a solution of a convex optimization problem. And we're going to write that this way. You minimize F0 of xt, u, and theta, subject to fi of xt, u, theta less than or equal to 0, and then a set of linear inequality constraints, right? And here I'm writing xt as the state, or a better term for it actually is the context rather than the state. State suggests something more than just the context. Roughly speaking, xt is just everything you know at time t and will inform your action, right? One thing important here I've slipped in are these parameters, the thetas, right? So the theta here, these are parameters, and they flavorize the policy. So I'll talk quite a bit about these parameters, right? So this is the idea. That is a COCP. And what we're going to do now is talk about why would you use a COCP, right? And actually, what it really comes down to is actually kind of interesting, and it's a very basic distinction. It's really the difference between procedural versus declarative. So procedural is where, a procedural policy is one where you actually work out exactly what to do in a given context, right? So for example, if it's a hybrid vehicle control, it might be a big table that says, if your battery is less than 22% charged and this and that, then do this. And if that, something like that. Or a very famous example would be PI. So here is a PI control. And it's basically just writing out what it does depending on the context. Now, in contrast, a declarative policy is kind of interesting. In a declarative policy, the way you do that is a designer articulates what she wants and requires. Those are literally the objective and constraints, and then lets the optimization solver figure out how to do it. So, and I know, we're all used to this. I think everyone, at this meeting would get that. I have had some hilarious conversations with old school people. And I remember one went like this. One said to me, you could probably guess who this is anyway. So one said to me, look, I know what to do if an airplane is rolling to the left, it's like tip up your right aileron or something like that. I was like, cool. And I said, yeah, well, here's how I do it. I tell an optimization problem, I like flying level. And then I give it a model of the dynamics. And and the person said to me, well, what does it do? I said, it raises the right aileron. He said, yeah, but I knew that anyway. So the point is that, but it's an interest. It's just a way to think about it. It's not deep, but this is often the confusion when someone says, what is the difference, right? So, okay. So let me start with the advantages of a COCP. Well, the first one is they are interpretable. We know exactly what they do, right? They respect constraints better than some posterior projection clipping, fixing things up, right? If you do LQR and then you clip your actuators to the allowed ranges, you'll get a policy, a control policy. It's actually probably not that bad, but something like this would do better. What's cool is you can also throw in tons. You can safety fence your policy. And what that means is you throw in a whole bunch of constraints, which are in normal operation simply not active. But they're sitting there very quietly and will not allow you to do something insane. The other one, as I already mentioned in the context of actuator allocation, is this very gracefully handles changing dynamics, availabilities, and failures, right? Because what happens is if the dynamics change, if there's some availability or a failure of an actuator or a sensor or something like that, then all you do is you change the optimization problem you're solving and you proceed, right? And they can be very effectively tuned. I'm going to say a lot about that in a bit. Now, so here's one thing you do hear from, and maybe from some people, is they'd say I'm not going to solve a convex optimization problem at 100 every 10 milliseconds. You got to be kidding. That's not, it's got to have 100.0% reliability, and it's got to be, I have to meet my real-time deadline all the time and so on. And it turns out that is a non-disadvantage because depending on the problem, of course, that's readily achieved. Can make them totally reliable. You can make the reliability 1.0. Actually, in some cases, you can even achieve division free, which is pretty awesome, because that means basically it's just not going to mess up. So, okay, these would be the advantages. And I'll mention something about the advantages. These are possibly controversial. Maybe they are. The first thing, something like a convex optimization control point, it never does anything crazy, like characterize a stop sign as a banana or something like that, right? So it's an extremely strong form of regularization, right? That is just, you know what it does, right? If you have an LQR controller, it's just not going to do anything stupid, right? Ever, period. The second, which I think is an idea that goes all the way back to the 1960s, early 60s, is the idea is that parameterizing a COCP is better than parameterizing the raw controller or policy, right? And that was stated with total clarity already in like 1961 and 62, where the basic idea is let's just do a linear controller. Let's say you're designing a feedback gain matrix K, and it's like 8 by 12 or something, right? It's just easier to mess with, let's say, Q and R. Those are the parameters in the LQR controller than it is to come up with a sensible 8 by 12 matrix. That's been stated in utter clarity, like in 1961, 62, 63. So people who do that kind of design actually think of it that way. Now, by the way, this is just, there's people I respect who don't believe that, and they say nonsense. I can parameterize my policy, and just do policy optimization or something. That's fine. But this is just, like I said, I believe this mostly. Okay. Next topic is going to be tuning. Yes.
If I take a convex problem like training an SVM, why would they never characterize, what was your example? Like monkey is a banana, or I forgot what you said.
Oh, I don't know. A banana is a stop sign.
Yes. Yeah. Why would an SVM not do that?
Well, first of all, that's not actually the context. I was talking about a controller, right? That solves a convex problem. But if you want, we can think of a classifier as a kind of controller, if you like. That's fine. And actually, there it's going to depend on your feature engineering, right? So, but if you don't do a lot of feature engineering, I can look at your SVM and I can say, look, it's whatever it is, it's monotone increasing in this feature, and we can just check, does that make sense, not make sense, and so on, right? Now, if you engineer crazy features, then you might as well have had a neural network in the beginning, right? So that would. No,
I guess the opposite direction is, if you don't engineer the features much, maybe the performance will be very robust, but the performance would be fairly low.
Absolutely. No, there's always a performance robustness trade-off. That's right. And so what we're looking for are things like, PID. That's a great success that we should celebrate. And that's something that's embarrassingly simple, delivers okay, even good performance across an enormous number of practical applications. Is it the best you can do? Well, almost certainly not. But in the robustness, performance, simplicity, trade-off, it's pretty attractive in my opinion, right? And I think these are the same. I'm sort of getting ahead of myself. That's going to be the final one. Let me see a little bit about tuning. So here's the design flow. Is you would first start by building a high fidelity simulator. You'd use real historical data. You would probably build a generative model or whatever, so that you can generate data that looks like past data, right? So you would almost certainly do that. Then you would implement code that evaluates the true performance objectives. And by the way, that does not have to be it certainly doesn't have to be the same as what's going to be in your COCP, right? It could be very complex, and we even have that in your example just now of classification, right? The true performance objective might be something like your error rate, right? And you're not going to optimize your convex optimization policy might do something like minimize a negative log likelihood of a logistic or something like that. Okay. You'll then choose a parameterized convex optimization based policy. And you'll tune the parameters until you're okay with the simulated performance, right? So that's sort of the general design flow. And now traditional tuning and tweaking, tweaking it has a slightly pejorative sound to it. Yeah, it sounds like someone who doesn't know what they're doing and they just put something together and they tried some parameters and they go, okay, we'll double that one, divide that one by 2, and then after they get bored, they quit. But tuning maybe is not pejorative. So the way this would work is you start with some reasonable value for theta and you'd simulate it, and then you update theta by hand, and then you repeat until you're either happy or you're bored or you're out of time, right? Or you could fire up a derivative-free method and then go to lunch and come back and it's done, 5,000 simulations and you have your parameter values, right? So, for example, I mean, this is actually how people use things like LQR, Kalman filter, things like that. It's always this way. You look at it, you run it into your complicated, fancy simulator, you evaluate the true objective, and you'd say, it was too, the actuator usage was too high. And you go, no problem. And then you just crank up R or some entry in the R matrix or whatever, and then do another one. So, okay. So this is the traditional method. It's been done for a long time. And